guys, and welcome to another calculus video. In this video we are going to be proving these 8 integral representations of gamma, which is the Euler-Mascheroni constant, which is defined as the limit as n goes to infinity of the harmonic numbers minus the natural logarithm. So h sub n minus natural log of n, limit as n goes to infinity. And of course, the Euler-Mascheroni constant is better known as the Euler-Macaroni constant, at least on YouTube, which is why I'm calling this video Macaroni Mayhem, because we're going to be going over a ton of different ways to prove it. Many of these are just repetitions, but some of them are entirely new integrals, so let's go ahead and get started. Now this first one is going to be a bit odd because what we need to do is we need to connect the Euler-Mascheroni constant with the gamma function. So we're using this representation of the gamma function, which of course you could, be a little bit upset that I'm using this unorthodox representation here, but I got to start somewhere. I can't prove it starting from nothing. So this is a formula right here for x gamma of x, or gamma of x plus 1, and it's the limit as n goes to infinity of n to the x times the product from k equals 1 to n of k over k plus x. So we take the natural log on both sides, and that actually turns this into an infinite summation right over here. So this n to the x comes out as x times natural log of n, and then we subtract the sum from k equals 1 to n of ln 1 plus x over k. Then we expand 1 plus x over k as a power series in m. So we get, or I guess not a power series in m, as an infinite series. So that's going to be rewritten as the sum from m equals 1 to infinity of negative 1 to the m plus 1 over m times x over k to the m. Then what we're going to do is we're going to take out this first term when m equals 1. So when m equals 1, we just have negative 1 right here. Or I guess we have we have positive 1 on the inside over 1 times x over k. And when we plug in, so it's times x over k. So when we go ahead and take that out, what we're just going to get is we're going to be subtracting the sum from k equals 1 to n of just 1 over k. So that's this right here, and so as you can see, and of course we also have this x on the top. So we have x times natural log of n minus x times the sum from k equals 1 to n of 1 over k, and this is just h sub n. So we have the limit as m goes to infinity of natural log of n minus h of n, which is just negative gamma, as you can see on the next line, all multiplied by x. And we have this leftover summation right here. And for this summation, we can actually go ahead and let n tend to infinity, because now this is just a normal infinite summation with no divergence or anything. So we reorganize the terms right here, and we get that natural log of gamma of x plus 1 equals negative gamma x plus m equals, the sum from m equals 2 to infinity of negative x to the m, zeta of m all over m. Differentiating, the derivative of the natural log of the gamma function is just the digamma function, so we get that digamma of x plus 1 equals negative gamma minus the sum from m equals 2 to infinity of negative x to the m minus 1, sorry, that's an m right there, times zeta of m. So when we go ahead and plug in x equals 0, we find that this is just going to go to 0 right here, since we have x raised to a positive power. And so that tells us that zeta of 1, digamma of 1 is negative gamma. Furthermore, gamma prime of 1 over gamma of 1 is negative gamma, since that's another definition of the digamma function, which means that gamma prime of 1 equals negative gamma. Now let's go ahead and calculate gamma prime of 1. So we take the gamma function right here, integral from 0 to infinity of t to the x minus 1 e to the negative t dt, which tells us that gamma prime of x equals the integral from 0 to infinity of t to the x minus 1 natural log of t e to the negative t dt. Now plugging in x equals 1 gives us this integral representation right here. Gamma equals the integral from 0 to infinity of e to the negative t natural log of t, and actually I forgot a negative sign right there, because of course this is actually negative gamma right here, so I'm going to go ahead and add in a negative sign in front. Alright, so that's our first one, and from here on out, they're going to be much more straightforward proofs in general. So this next one right here is just a reorganization. It's actually just a reorganization of the other one right here. We have the integral from 0 to 1 of ln 1 over x dx, and after u equals negative ln x, or which is the same as ln 1 over x, we get x equals e to the negative u, and dx equals negative e to the negative u du. And we end up with negative integral from 0 to infinity of e to the negative u, natural log of u, du. which is just the Euler-Mascheroni constant, gamma. Now, number 3, I think is really fun because we get to use the Mellin transform, which actually is true about several of these, because the Mellin transform, it's really easy to end up getting Euler-Mascheroni constants out of it. So first, we're going to calculate this, which is called the Bose integral. It's really, really straightforward. The integral from 0 to infinity of x to the s minus 1 over e to the x minus 1. We multiply by e to the negative x on the top and bottom, and apply the power series for 1 over 1 minus x. So we end up with the sum from n equals 0 to infinity of the integral from 0 to infinity of x to the s minus 1 minus n plus 1 times minus e to the n plus 1 times x, negative n plus 1, sorry. And this gives us the sum from n equals 0 to infinity of gamma of s over n plus 1 to the s, which is the same as gamma of s times zeta of s. So going back to our integral right here, we're going to actually sort of parameterize this integral. We're going to create another integral called I of s, which is the integral from 0 to infinity of x to the s minus 1 over e to the x minus 1 minus x to the s minus 2 times e to the negative x dx. And notice that if we let s go to 1, we get back our original integral right here. So limit as s goes to 1 of I of s is just going to be I. And here, so evaluating I of s directly, we get that I of s equals this first part, which is gamma of s zeta of s, and the second part, which is just gamma of s minus 1. Reorganizing, we get that we're getting the limit as s goes to 1 of gamma of s times zeta of s minus gamma of s over s plus 1 using the functional identity for the gamma function. Then we factor out this gamma of s. Since limit as s goes to 1 of gamma of s is just 1, it doesn't affect the value of the limit. And so we just get the limit as s goes to 1 of gamma of, or zeta of s minus 1 over s minus 1. Now, if we go ahead and get the Laurent expansion of the zeta function, which again is something that I'm not going to go through right here since it's very extensive, but essentially this is where this integral representation comes from, we get that zeta of s equals 1 over s minus 1 plus gamma plus some other terms which are of order s minus 1 and above. So when we take the limit as s goes to 1 of this, all of these are just going to go to 0, and we're just going to end up getting zeta of s minus 1 over s minus 1 is just gamma. And that is the answer to that integral as well. Surprise, surprise. Integral number 4 right here is just a sneaky little reorganization. We have integral from 0 to 1 of 1 minus e to the negative x over x minus the integral from 1 to infinity of e to the negative x over x dx. So we'll just do integration by parts on both parts here. We're going to integrate x and differentiate 1 minus e to the negative x. And we find that both of our sort of terms right here go to 0, and this side we integrate x and we differentiate e to the negative x. We actually end up with the integral from 0 to 1 of e to the negative x ln x dx, and the integral from 1 to infinity of e to the negative x ln x. And eventually we add those together to get the integral from 0 to infinity of e to the negative x ln x dx, which is just the Euler-Mascheroni constant, gamma. Here's another really fun one. This one I've actually done in a previous video since it was Putnam integral a long time ago. So we have the integral from 0 to 1 of 1 over natural log of x plus 1 over 1 minus x. And what we're going to do is we're going to sort of multiply and divide by x minus 1 on the inside and outside here. So we get integral from 0 to 1 of x minus 1 over ln x minus 1 all times dx over x minus 1. And the reason we want to do this is we're going to use this identity right here. X to the a minus 1 over ln x actually equals the integral from 0 to a of x to the b with respect to b. So we go ahead and plug this in, and we get the integral from 0 to 1 of this little expression right here. So I also wrote negative 1 as the integral from 0 to 1 of negative 1 db. And this allows us to combine all of this into one integral right here, which is the integral from 0 to 1 of x to the b minus 1 db. So we end up with this double integral from 0 to 1 and 0 to 1 of 1 minus x to the b over 1 minus x dx db. Notice I changed the order of integration here. And then we use the fact that digamma of x equals negative gamma plus the integral from 0 to 1 of 1 minus t to the x minus 1 over 1 minus t. This one's super easy to prove if you use the series representation of the digamma function. And so here, notice that we have b rather than x minus 1, and we don't have this negative gamma right here. So what this means is that this is actually going to be equal to digamma of b plus 1 plus gamma, which as you can see I've substituted in right here, Then we just integrate it from 0 to 1. Remember that the integral of the digamma function is natural log of the gamma function, which when we evaluate gamma of 2 and gamma of 1, they're just the exact same thing, so this is just going to end up going to 0, and we just have the integral from 0 to 1 of gamma, which is just gamma, of course. Number 6 is another really fun one because we get to use the Mellin transform again. Again, the Mellin transform is a really underrated tool, and it's something that I'm definitely going to have to make a video on soon because I don't see people using it all too often. So again, we're going to rewrite this as the Mellin transform I of s equals the integral from 0 to infinity of x to the s minus 1 times 1 over 1 plus x to the k minus e to the negative x dx. And we're taking the limit as s goes to 0 because this gives us back our original integral. So we can sort of split it apart. Note that we can't actually split apart these two integrals because then our integral would really diverge as s nears 0, of course. I guess we still could do that, and then since it will converge for s greater than 0, but it's good to just keep stuff uh, all together so that we can make sure it converges. So we're going to use this identity right here that the integral from 0 to infinity of x to the a over 1 plus x to the b dx equals pi over b cosecant of a plus 1 over b times pi, which I've proved in many, many videos. So when we go ahead and evaluate this, we get that our I of s equals pi over k cosecant s pi over k minus gamma of s. Now we take the limit as s goes to 0, and this is where it gets interesting. So what I'm going to do here is I'm going to multiply on the top and bottom by s, because then I can use L'Hospital's rule. So multiplying on the top by s gives gamma of s plus 1 right over here, and that's just because s gamma of s equals gamma of s plus 1. And right here we can rewrite this as s pi over k over sine s pi over k, which is the same thing as 1 over sinc of s pi over k, because the sinc function is just sine x over x. And now we're going to differentiate on the top and bottom, and notice on the bottom we just have an s, so that's just going to become 1. On the top we have 1 over sinc of s pi over k minus gamma of s plus 1. And so what we're going to get is the derivative of 1 over sinc s pi over k, evaluated at s equals 0, minus gamma prime of 1. And the interesting thing about this right here is that the sinc function sine x over x is an even function, which means that 1 over the sinc function is also an even function. And this s pi over k is the same thing as 1 over sinc of s, essentially, in terms of being an even function. So this is an even function. And a really, really cool tool for evaluating a lot of limits like this, involving the Mellin transform, is actually noticing that if a function is even, I've sort of drawn a visualization here. This is sinc of x, but if a function is even, then its derivative at 0 actually has to be 0. And you can not only show this using power series, but you can also show this just by the basic logic that the value just to the right and the value just to the left needs to be exactly the same, which means if you were to draw a secant line, the secant line would have to be horizontal, and as you get closer and closer to 0, that secant line becomes a tangent line, which also has to be horizontal, meaning the derivative has to be 0. So the derivative of an even function evaluated at 0 is always going to be 0, so we don't need to worry about this, and we just have negative gamma prime of 1, which is gamma. Number 7 is another one that I've done in a previous video, but, doesn't harm to do it again. We have 2 times the integral from 0 to infinity of e to the negative x squared minus e to the negative x all over x dx. And notice that we have sort of two very similar expressions here. They're just differing by this 2 in the top, so we're going to go ahead and parameterize and use Feynman's trick. So we get that I of v equals 2 times the integral from 0 to infinity of e to the negative x to the v minus e to the negative x all over x dx. Differentiating with respect to v, we get I prime of v equals 2 times the integral from 0 to infinity of negative x to the v minus 1. The v minus 1 just comes from this x on the bottom, times e to the negative x to the v times natural log of x dx. So we do u equals x to the v, which means that du equals v times x to the v minus 1, which looks a lot like this. We just need to divide by v. So we get 2 times the integral from 0 to infinity of negative 1 over v, e to the negative u, times natural log of u to the 1 over v, because remember this was natural log x. So we get negative 2 over v squared, integral from 0 to infinity of e to the negative u ln u du, which is just the same as 2 gamma over v squared, which tells us that I of v is equal to negative 2 gamma over v plus c. But we know that I of 1 is going to be 0, so if we plug in 1, everywhere, we should get that 0 equals negative 2 gamma plus c, which means that c is just 2 gamma. I of v equals negative 2 gamma over v plus 2 gamma. Also, we know that I of 1 is 0 if you just go ahead and look back at our definition of I of v. And that means that I of 2 is just 2 gamma minus gamma, which is just gamma. And finally, number 8 is really, really simple. So we have, this one's a little bit interesting since we have integral from 0 to 1 of h sub x dx, and h sub x represents the fractional harmonic numbers. So if x were a positive integer, it would just be the same as a harmonic number, but it also interpolates and has values for all fractional numbers, and it's a continuous and differentiable function, which is nice. So h sub x equals the sum from k equals 1 to infinity of 1 over k minus 1 over k plus x, or the sum from k equals 1 to infinity of x over k times k plus x. And something interesting about this is because of the properties of the fractional harmonic numbers, they're basically defined by the fact that they need to be continuous and differentiable, and f of n plus 1 has to be f of n plus 1 over n, and that actually matches up exactly with what the digamma function is. So the digamma function can also be defined as negative gamma plus h sub x minus 1. So what this means is that h sub x is just equal to digamma of x plus 1 plus gamma. So when we integrate from 0 to 1, we already did this one before, and this is just going to be gamma. And that is all 8 representations on Wikipedia for the gamma function, or sorry, not for the gamma function, for the Euler-Mascheroni constant. This was a viewer suggested video. So if you guys have any suggestions, please feel free to throw them down in the comments or join my Discord and leave the suggestions in there, because I'm always looking for new video ideas, and I want to see what you guys want to see so that I can make videos that you enjoy. What other formulas for the Euler-Mascheroni constant do you know? Go ahead and tell me in the comments if you want. And yeah, I hope you guys enjoyed the video and learned something, and I'll see you next time. Thank you so much for watching. Bye.